Okay, so hi everyone. We would like to welcome you all to this talk of the IEEE GRSS-APS-SSCS student chapter at the University of Southern California. Today, we are pleased and honored to have this talk presented by Professor Cynthia Furse, entitled History and Future of Implantable Antennas. Dr. Cynthia Furse is a fellow of the IEEE and the National Academy of Inventors, and is a professor of electrical and computer engineering at the University of Utah. Her research interests are the application of electromagnetics to sensing and communication in complex lossy scattering media, such as the human body, geophysical prospecting, ionospheric plasma, and complex wiring networks. Dr. Furse is a founder of Live Wire Innovation Incorporation, a spin-off company from her research, commercializing devices to locate intermittent faults on live wires. She has taught electromagnetics, wireless communication, computational electromagnetics, microwave engineering, antenna design, introductory electrical engineering, and engineering entrepreneurship, and has been a leader in the development of the flipped classroom. Dr. Furse is an associate editor for the Transactions on Antennas and Propagation, chair of the IEEE Antennas and Propagation Society Awards Committee, a past administrative committee member for the IEEE AP Society, and past chair of the IEEE AP Education Committee. She has received numerous teaching and research awards, including the 2020 IEEE Cento Tai Distinguished Educator Award. Professor Furse, we would like to welcome you again, and the floor is yours.
Well, thank you very much, and I am delighted to join you tonight. The picture behind me is very much the picture of Salt Lake City today, as we had a beautiful giant snowstorm. So it's really a nice place to be right now. And so the topic that I've chosen is a history and future of implantable antennas. And what I'd like to do is spend some time talking about some of the really basic electromagnetic concepts and how they have gone into the implantable antenna designs. So we may look at new publications. I mean, there's a new antenna every week, but there are some basic tenets that have really driven this technology from the past and really are driving it into the future as well. I've put my lab website here, emlab.eng.utah.edu. If you would like to be able to find some of our publications, that's where I store most of the publications these days. So I am from the University of Utah. Here's a picture of where Utah is, of course, in the United States. Our buildings are excellent. We have a really nice facility. If you happen to be through this way, please do come and visit. We'd love to show you around. So we're going to talk about implantable antennas. And of course, those are used for many different medical implants. These are just a few of the technologies. And of course, more can be enabled if we are able to make our devices progressively smaller. We're going to talk about cardiac pacemakers, the artificial pancreas, cochlear implants, retinal implants, and brain stimulators, and how the antennas are needed in each of these applications. So let's begin with a cardiac pacemaker or defibrillator, which is the largest quantity of implantable devices that are used today by far. The vast majority of these are pacemakers. So the pacemaker has a battery pack. It's kind of just shown up there in the shoulder. It's actually implanted not very far, just under the pectoral muscle, so not too deep in the body. It's not below it's above the ribs, not below the ribs. And that's the battery pack. It holds the little computer, all of the electronics, and the lead plugs into that. And then they have to do open heart surgery in order to actually attach the lead into the heart itself. So the lead has 2 electrodes, or more sometimes, but 2 electrodes generally. They'll be attached on either side of the heart, and that will stimulate the heart, shock it in a certain pattern in order to keep it beating the way that it should. Now, a significant change has been the leadless pacemaker, which you see on the right. That can be used for some applications, but not all, and there are hopes for this to be expanded in the future. The leadless pacemaker requires no significant surgery. Instead, the pacemaker is a small incision is made in the groin, and the pacemaker is pushed up through the femoral artery that's there. And so you don't have to do open heart surgery at all. It's very small. It's about the size of a capsule, just a little, large pill capsule. And so the battery, the computer, and all of the stimulation devices have to be enclosed in that single capsule. So again, that will work for some applications, but not all. It gives you an idea how things are going to move from relatively large, complex devices into smaller devices. The artificial pancreas is a device that has a glucose sensor, so it's sensing the blood all of the time. And then it has a reservoir in which insulin is stored. And so it releases insulin according to the amount of glucose in the blood. So whether someone's been exercising, eaten a large meal, might have been ill, taken some other medications, these can change how much insulin is needed by someone who is diabetic. This device is extremely good at being able to monitor the diabetes itself, the blood and the amount of sugar that's in the blood, and being able to respond accordingly. In addition, there's an antenna that transmits this information out to a hip-mounted cell phone in this case, and the person who is using this device can not only monitor the amount of insulin that remains in their reservoir, but also how this is behaving with their body. So they can see, oh, I had a spike in blood sugar, so there was also a spike in insulin. Doctors, of course, can use this information as well. So the artificial pancreas also has to have essentially an antenna to communicate out with a hip-mounted battery pack. The artificial retina, something that you should be familiar with because of John Luca's work at USC, has a camera that takes a picture of the scene in front of the person. It converts it to electrical signals and then converts those electrical signals into stimulation that is it is injected in the back of the eye through a series of electrodes. So there have to be a series of antennas in here. One of the antennas that is most important is from the outside of the body to the inside of the body to take the information in wirelessly so that you don't have to have a wired link there. The cochlear implant is similar, except it's for audio signals. So it has a transmitter and a microphone and speech processor outside. Those are generally on the back, held on the back of the ear, just with a little clip. And then there's a transmitter that transmits inside, so under the skin, and then electrodes implanted in the cochlea, kind of a long, skinny thing will be implanted into the spiral shape of the cochlea, and that will have a series of electrodes that will stimulate the ear. So both in the case of vision and the case of hearing, there's quite a bit of processing as well that's going to tell each of these electrodes what stimulation is needed in order for that person to hear or to see. Medical implants are also used for deep brain stimulation, or DBS. The same battery pack that is used for the pacemaker is implanted in the shoulder, so the battery pack's in the same place that it would be for the heart. And then the cable, instead of being run to the heart, is actually run up under the skin through the neck, over to the surface of the skull, where an electrode is placed deep. So see this kind of deep, long electrode there? The deep electrode is placed in a hole in the skull. You have to drill a hole and press the electrode in, and then the connection is made to the wire there. So the stimulator is going to stimulate, again, different parts of the brain depending on the disease. Some of the diseases that have been treated extremely well with this are Parkinson's and tremor-based diseases, as well as epilepsy and dystonia. And now some of the psychological diseases, such as depression, that might be so bad that it doesn't respond to drugs, and possibly other psychological disorders, have all been responsive to this deep brain stimulation. So these are some of the applications for medical implants that are pretty exciting today, and more are coming. Now, many of these are based on stimulation or reception. So that we know we can stimulate and receive things with electrodes. This is an example of the Utah electrode array. It has 10 electrodes on each side, so for a total of 100 electrodes. It's made from a single piece of silicone, which is etched, much like a wafer might be if you were making a chip. And so each of these is a very tiny electrode, very sharp, and biocompatible. Now, at the moment, these are not wireless devices, they are wired. So if you see kind of this set of wires that's coming off here on the side of the penny, there are 100 wires that are coming out, and they do have to be directly connected to something in order to either stimulate or receive. This does localized nerve stimulation, and it can repair or replace damaged nerves. But this device is not today wireless, it is wired. And so that's a consideration. Now for wireless technology, here's an example of the cochlear implant. And we do have to have a wireless link from inside where you're going to attach onto your stimulating device, and outside where you're receiving your audio signals. Now, today, there are two reasons that we would need to do this. One is for telemetry, and that's to either transmit or to receive data. And the other is for wireless power transfer, or WPT, and that's to transmit power. Now, normally that power transmission would just be to recharge a battery, so it can be kind of like trickle charging. You don't have to have a huge amount of power at any given time. So you can recharge kind of at your leisure when you choose to recharge. And also you don't have to send very much power at any given time. Now, today, the most common way that this is done is with inductive coupling. And that's where you have two coils. And of course, one coil can be used to transmit energy down and transmit energy up. Here's an example of a coil that's done with an 18 kilohertz with a 300 kilohertz sync signal. Now, we know about wireless inductive coupling. And in this case, a current produces a magnetic field from the first coil. The magnetic field from the first coil is picked up by a second coil, and the second coil turns that back into a current using a rectifier. So this is by far the most common method used today. But in electromagnetics, there are some facts that happen here that really limit the ability of this device. So first of all, we do know that we are directly coupling two magnetic fields, and they have to literally be picked up by these coils. And since they spread out, like if you move the coils apart, the magnetic field is going to flare out, and not all of the magnetic field from the first coil would then be picked up by the second. So that limits the distance that these two coils can be separated just because of the fringing of those magnetic fields. We also know that alignment's a very important consideration, because as your magnetic field is produced by your first loop, if you misaligned your second loop, or if you tipped it even, you wouldn't be picking up all of the magnetic field. Again, you'd be wasting a lot of the energy. So those are two things that happen because of the physical business of making a magnetic field with a coil. We also know there are limitations with frequency and data rates with this method, and there's a significant loss in the coils and the circuits, so there are some efficiency problems as well. But this has been used successfully, and in many different applications. It is commercially available today. It's in most pacemakers and other devices. Here's just an example from 1997 for a cortical visual implant. Now, that was in the very early days of implantable electrical devices, 20 megahertz device, and it was powered with a 5 millimeter diameter power coil, which was printed. So it was gold ink on a flexible substrate, and that's all good, but it has limitations in efficiency because as you print devices, they aren't quite as conductive as if they had been straight gold. And you would think that the more and more coils you would have, the better, but there ends up being a limit to the number of coils based on the efficiency, the amount of resistance that you get just because of essentially having too much printed wire. The smallest coil that I can find in the literature, and correct me if you find something smaller, is this one that's done by Murati et al. And that is a 1 millimeter coil that's just basically tape on a small Teflon cube, and very, very tiny. But as you can imagine, the challenge with this, of course, is being able to make, to be able to pick up enough field with this very, very tiny coil, and also to align and place it properly so that you're able to pick everything up. So here are a couple of examples of really cool coils that are used today. And do realize inductive coupling is successful. It is used today, but it does have limitations in distance, and it also has limitations in data and bandwidth. I got into this area in 1999. I had an undergraduate student, his name was Sam. This is literally his pacemaker that was inside his body. Yes, they put it through a device to clean it up before they gave it to me, but this is literally Sam's pacemaker. He was a climber. He was an undergraduate in my electromagnetics class, and he had to miss class for pacemaker replacement surgery. At the time, they didn't really know if your battery was going to be dead or not. And in his case, his battery was fine, and he could have gone another couple of years. And he was like, dang, I really was sorry that I had to miss class for this pacemaker surgery because they didn't have a good enough communication system with this pacemaker that he didn't have to go to the doctor all the time for these types of updates. So he wanted to do a senior project related to his pacemaker. So we evaluated what it would take to put an antenna that would give you a further distance so that maybe his pacemaker could communicate to something on his hip. Well, electromagnetics, again, has several important just rules that we know about that really play into implantable antennas. So just think about the most basic antenna that we know about, the dipole antenna. Let's talk about a half-wave dipole. Of course, that's two arms with a feed point in the middle, and we know that a higher frequency is going to have a smaller antenna. For example, at 20 megahertz in air, a half wavelength dipole would be 41 centimeters long, and at 403 megahertz, it would be 5 centimeters long. So a smaller antenna comes from using a higher frequency. Now, the pacemaker that Sam had was about 4 centimeters across. Many of these devices are shrinking today, and they range between 2 to 4 centimeters in size. So at 403 megahertz, we're starting to get down to a size that becomes realistic to potentially be able to put it on the size of this pacemaker. The 20 megahertz, although we certainly know that we'd be able to transmit further, it's not going to fit on this pacemaker. Well, of course, the trade-off with there is that as you go to a higher frequency, you have less depth of penetration. Here's the distance, of course, the exponential curves in skin for a 20 megahertz antenna and a 403 megahertz antenna. Yes, we'd like to have that 20 megahertz antenna in order to get deeper depth of penetration, but the 403 megahertz is giving us something reasonable. So there is a trade-off between antenna size and frequency and depth of penetration. Now, this became important in the decision about which telemetry frequencies to approve. So when you have a frequency for something implantable, you certainly don't want to have lots of consumer electronics on that same frequency. You want to have a dedicated band. At first, we were using the industrial, scientific, medical, or ISM bands. These were established in 1947, and they have many applications. Some of the frequencies that are closest here, closest related, would be 433, 915, and 2450 megahertz. And you see a lot of devices, including medical devices, in those ranges because of the ISM bands. Now, also note, these are bands, because scientific, that you can do your research with. So we are actually going to choose a 433 megahertz band that's going to be close here because it's a band that we can legally work with in our lab. But in 1999 and then updated in 2009, a dedicated band, the Medical Implant Communication Services, or MIX band, was established. It's 402 to 405 megahertz. And so it's on the good side of the trade-off between bandwidth and frequency. It's a high enough frequency that we're able to make a relatively small antenna, but it's a low enough frequency to have at least a moderate depth of penetration. So that's why the mix band was established. There was a tremendous debate going on at this time. I was in graduate school watching this debate happen, and one of my faculty members, my advisor, Om Gandhi, was directly involved in the decisions and the debates about what band to choose. And it really was the trade-off of size versus depth of penetration. It was established in 1999, and then it was expanded and renamed the Med Radio band, and it's now 401 to 406 megahertz. And this is an international band that's available, and there shouldn't be anything else to interfere with there. Also, that means that if you are working in this area, you shouldn't use this band in your research lab. In case someone came in who had a medical device working in this range, you wouldn't want to be experimenting with an antenna. So we still work with 433 megahertz because it's close, but it shouldn't be interfering with the mixed band devices that someone might have in the lab. Now, there was another really important thing to consider, and that's the specific absorption rate, or SAR guidelines. These were established about that same time, 1995. The US FCC established the ANSI IEEE C95.1 SAR guidelines. These were actually very much related to the cell phone guidelines. So, I mean, the cell phone is what kind of drove this question, and it ends up being important in implantable devices too. But this particular guideline was driven more by cell phone concerns than it was by implantable devices. However, it applies to both. In this case, it was really hard to decide, how are you going to decide if electromagnetic fields were safe or not? Electromagnetic fields do not destroy cells like X-rays do. They don't break cells, so consequently, they don't cause cancer, at least not in that way. And there's no real indication that they do cause cancer. So if they don't cause cancer, how should we decide what is safe and what is not? At the time, we weren't even really sure how to decide at all. So again, this was a really interesting debate. The way the SAR guidelines ended up being established was based on heating and cooking. So we know that certainly it'd be dangerous to cook the cells in your body, right? You destroy the cells by cooking them. And so you don't want to overheat. So they went down several factors of the amount of energy that could cause heating distress in the body. And that's the SAR guideline that they used. So the SAR guidelines are literally based on how much heat your body can handle and dissipate without heating, without overheating. So a 1 gram SAR of less than 1.6 watts per kilogram was established. So a 1 gram SAR means that you take a cube about the size of the end of your finger, that's about 1 centimeter square, it's about 1 gram. and you average the SAR over that an area of that size, and it needs to be less than 1.6 watts per kilogram. I also put plus and minus how much here. This is a really interesting thing. So if you are evaluating implantable devices of any kind, you're probably using some kind of simulation tool. FDTD, like Gianluca is using and I have used as well, is one of the most common ways. There are finite element methods also, and a few other techniques. So suppose you're using a computational method, or you might even be using a measurement method. How do you expect that this is going to be perfect every time? Certainly your computer simulation is going to give you the same results every time. But if you change the size of the head just a tiny bit, your ear a little bit different than mine, your head a little bit different, maybe they implanted the device just a tiny bit in a different way, closer, further, whatever. The tissue properties, the electrical properties of tissue in your body change from time of day, from morning to night. They change from me to you. They change with age. Gender, sex, all of these things change the electric fields, the electric properties of your body. So although we're doing a simulation, and although we're doing a good simulation, we cannot do a perfect simulation for every case. So there is going to be a certain amount of variability. And in fact, that also has to be considered in the SAR guidelines, whether you're doing measurement or whether you are doing simulation. So you have to evaluate the amount of uncertainty that you expect in your measurements or that you expect in your simulations. So if you've taken classes where your faculty might have harped on what's the uncertainty in this numerical method, that is part of what goes into the SAR guidelines. But uncertainty in the model that you may use, in the tissue properties, in the location of your source, those are all uncertainties that have to be considered as well. So I put this in red. Uncertainty is something I'm very, very interested in, and it turns out it's really important, and it is part of the legal SAR guideline at this point. So the US-FCC established this in 1995. It was followed fairly closely by Europe, but the Senelec guidelines go for a 10-gram SAR. That's about the size of the end of your thumb, and that's less than 2 watts per kilogram. And why one versus the other? Well, anybody's guess. It was hotly debated, and either of these would have been appropriate guidelines. There is no strong reason why you should go with 1 gram versus 10, 1.6, maybe even versus 1.7. So these guidelines do have a certain amount of uncertainty in them as well. And these are the 2 guidelines that are most commonly used. These were later adopted, one version or the other, by most countries in the world. Okay, so we've talked about frequency, we've talked about size, we've talked about SAR and specific absorption rate. Now let's look at what we might do for an antenna. Well, along about this time, the planar inverted F antenna became very popular for cell phone applications, and not surprisingly, for implantable devices as well. The idea of a planar inverted F antenna is that you start with a ground plane. The pacemaker battery pack, which is made out of titanium, is an excellent ground plane. Not very easy to glue or solder to, but it's an excellent conductive ground plane. And then you have to make an antenna on top of this, or inside of it, either one. In this case, we were looking at being on top. Now the planar inverted F, the planar part means the top part is planar, and the F, see how I kind of outlined this F shape? So it's inverted F. So you're going to have a ground pin and a feed, and they could be on either side like this, but typically your ground pin would be on the end and your feed would be in the center, something like this. And the shape of the antenna radiator could be many different shapes, and let's assume that we want that to radiate up away from the pacemaker. So this is how a planar inverted F antenna could be installed on a cardiac pacemaker device. So here's Sam's pacemaker. Again, think 2 to 4 centimeters. And we made a shape of this out of aluminum so that we could build antennas on top of it. But if I were to put this in the body, the radiator would just get squashed against the titanium. And so you need to use a substrate. The substrate's going to serve 2 purposes. One of them is mechanical, literally to just hold the radiator up so it doesn't get squashed. And the other is electrical, because if you increase the dielectric constant of the substrate, you can make an even smaller antenna. What that does is it decreases the wavelength in that substrate material. And so your antenna can be smaller and still be electrically the same size at that frequency. So if you use a non-conductive substrate, you want to have the lowest conductivity that you can. So a really good insulator. You can use it to hold up the radiator physically. You can use it to help adhere this to the pacemaker body. And you can use a larger dielectric in order to be able to reduce the size of your antenna. So now what's going to happen is your half-wave dipole could have a ground pin, making it a monopole instead of a dipole. That cuts the size right there in half with the feet off to the side. And that makes it act as if it had a virtual antenna or a copycat on the other side, something like this. So you can basically cut your half-wave dipole in half by using this grounded feed. And then the substrate material is this white stuff. This is a Teflon that's on top of our device. So you need it's not a zero thickness, it's a measurable thickness, significant thickness, but it's used to hold the antenna in place as well as to reduce its electrical size, or reduce its physical size for its electrical shape. Well, now let's talk about the shape of the antenna. So the shape of the planar part of the antenna could be many different things. The coiled up design has the advantage that it's kind of like taking your dipole antenna and literally just rolling it up and making it physically take less real estate. So you could roll it up or you could fold it up. A rolled up design would be a spiral, and a folded design would be like a serpentine. Like, which one works better? Well, when we looked at the current distributions, which you see here, you can almost see why the spiral would be better than the serpentine. Now, when you roll these arms up, yes, the arms do couple to each other, as you would expect in anything electromagnetic. So we do get coupling between the arms. In the case of the spiral, however, an area with low current is coupling to an area with high current. In the case of the serpentine, two areas with high current are coupling to each other. That tends to result in more interference and therefore more change and actually reduction in the effective length of the antenna. So it turns out that a spiral antenna is actually only slightly better than a serpentine for implantable devices. So this was an example of one of the early spiral and serpentine antenna design papers that we worked on. Well, now let's see what might happen if we adjust the feed and the ground pins. Well, what we know about dipoles and monopoles is actually going to guide us here. We know that we can tune both the frequency and the matching by where we would put the feed in the ground if we were doing a monopole antenna. And so the same thing applies here to this implantable antenna. As you slide the ground and you slide the feed, you can slide them both to left, you can slide them both to right, you can separate them. You can actually adjust the frequency just a little. You can adjust the frequency of the antenna, and you can also adjust its matching. So that was a pretty cool thing. You can see on the bottom where I'm showing you the blue line, that's what happens if you move the ground. And the red is what happens if you move the feed. So we can do a little bit of antenna tuning just by moving the feed and the ground. Okay, so we've got a planar inverted F antenna. It's a cool design, kind of really popularized throughout the 1990s. And we're going to use a substrate material in order to shrink it and also to hold it in place. We're going to adjust the ground and the feed in order to be able to tune up our antenna. And we've already decided that one decent design for our radiator might be a spiral. Well, now what happens when we drop that whole thing into the body? Now, the body is basically like salt water. We're kind of a bag of salt water. And so it has a dielectric constant, epsilon r, of something around 60. Most of our tissues do, 40 to 60. And that actually shrinks our antenna too. The body is basically a superstrate material around this radiator, and so it's shrinking the antenna, which is great. The trouble, however, is that it's also very conductive. Unlike the substrate, which can be made a good insulator, the body is a very strong conductor, and so it's going to short that radiator right out. That makes the radiator act like it's very tiny, and that's not what we had in mind at all. So we need to be able to prevent the shorting out of this radiator, even while we take advantage of the fact that body tissue is going to make us be able to use a smaller antenna. So we use a superstrate material. Now the superstrate is also going to be an insulating material, or it can actually be partially insulating. So it's okay if it's partially conducting, it just can't be strongly conducting. In some cases, we tried a superstrate material that had salt in it, and the salt drew the fluid from the body into the salt pockets, the little spots where the salt was when we produced the superstrate, and it made it so that we were kind of able to grade the body in towards the radiator. Worked okay. But again, the superstrate has a larger dielectric, it's going to shrink our antenna, that's good. And we do need it to at least partially insulate the radiator from the body. So these are kind of going to be the parts of the planar inverted F antenna in the body. Now let's talk about the effect of these. Oops, what did I just do? Okay, let's talk about the effect of the substrate and superstrate materials. So the substrate's blue, the superstrate is green, and you can see that as I change the dielectric constant of both of these, I'm able to use either a higher frequency, lower frequency, or I can change the size of my antenna. So using a higher dielectric constant means I can use a lower frequency, or that I can use a physically smaller antenna for the same frequency. The substrate, you can see, does not do an awful lot to the S11. It doesn't change my matching too much, but boy, the superstrate changes my matching a lot. So we have to be a little bit careful in our trade-off on the superstrate particularly, that we can't use as high a superstrate dielectric as we might like, because it also starts to detune the antenna and makes it not match as well. Now, there have been several papers about spiral and serpentine PFA antennas. Here's just another one from 2004 from the Ramaswamy group. And in their case, they were experimenting with all the different parts of that spiral. Like if you went up just a little, over just a little, how did these matter? And in fact, they did, as you can imagine. So you can change the size and the shape like this. You can make them fat and skinny. And it does, in fact, allow you to tune up the antenna in different ways. Not at all surprising, because we would expect that for any type of antenna. Now, let's go with one more electromagnetics fact. We might think that it's the metal part of this thing that is radiating, right? We might even picture that this antenna is radiating right down the middle of that spiral. But in fact, like all antennas, it really is the edge of the antenna that is radiating. So in the case of the top spiral, for example, you'll notice that the outside edge, this outside part right here, and the inside edge are slightly different in length, and they are both radiating. These both contribute to different frequencies and, in fact, the bandwidth of your antenna. If you make them even more different, like this one, see how this outside is so much longer than the inside, you might end up with a broader band or maybe even two different bands. So one important thing is to remember that the edges of the antenna are radiating more than the middle parts of the antenna, the fat part of the antenna itself. And there's another important feature here. Look at those corners. Do you think those corners radiate? Oh yeah. The corners on all of these antennas also have significant radiation. Now, you may or may not want that. It may or may not cause coupling and coupling problems, coupling advantages, but be aware that with all of these implantable devices, like all microstrip antennas, it's the edges and also the corners that are doing the most of the radiation for you. Okay, so those were a couple of examples of spiral antennas. Here's an example of a serpentine antenna that's a PFA with a ground plane and a feed just like this from Topsical's group. Again, substrate, superstrate materials both needed. This one is used for continuous blood glucose monitoring. But wait a minute, this is not actually an antenna intended to radiate. This is an antenna that's intended to sense the immediate environment. And so it wants to be paying attention to things that are closer to it. And in fact, the serpentine is a better sensor than it is a radiator. And that happens a lot with antennas. If an antenna is a really good radiator, it means that it's sending things far away. It also means that it would be sensing things far away. But if you want to have a sensor for something close, you don't really want it to be a fantastic radiator. You'd like it to be keeping its fields close by. And the serpentine antenna does that well. So here's an example of a continuous blood glucose monitoring in the 402 to 405 megahertz, and also 2.4 to 2.48 gigahertz range. So those are very close to the frequencies that we would use for communication too. Here's another spiral PFA. This is put on a circular pacemaker package. This is from 2011. Again, adjusting up the sizes in order to be able to tune it up really well. And then from there, some really cool things started happening in the year 2000, around the year 2000. In previously, like all of these examples, these are flat, planar, inverted F antennas. But in the 2000s, we started having some really fantastic expansion of computational electromagnetics. So instead of just doing the 2D, the small, the really simple, we started being able to do things that were in 3D really well. Not only were we able to manufacture them better, but we also were able to compute them better. And the computational electromagnetics was able to do things with much more precision. As the computers got bigger, the codes got more efficient, we were able to have just some really big advantages. And that resulted in several three-dimensional antennas in the 2010 period. Here's an example of one that you can see is a series of planes here on the left. See, it's a series of planar antennas, but you have vias going up connecting multiple planes. So this is a three-dimensional spiral meant for a pill, and it would have a complete integration with a very small implantable device. It also would be multiband because it had multiple points that you would have feeds and grounds. And it was working in both the 402 to 405 and the 2.4 to 2.48 gigahertz bands. Here's another flexible loop antenna that's printed on a flat flexible substrate and then wrapped around the knee. So this three-dimensional antenna was pretty cool. And then here's a differentially fed flexible antenna that would also go on a very small battery pack. Again, notice the frequencies, 402 to 405 and 2.4 to 2.48 gigahertz. So this is a very small antenna in a 3D package. So three-dimensional antennas became a thing in about 2010. So don't forget, when you're looking at antennas, that we are not limited to planar designs at this point. Well, there are many, many other shapes. Here's just another example. This is a genetic algorithm antenna. This is a PIFA, it is planar. Notice there's a feed, there's also ground on this antenna. And this is where you take two antennas with this kind of random waffle design. You call one the mother, the other the father, and you breed them. If they both have copper there, then the children will have copper in that location. If they both have air, the babies will have air. And if mom has copper and dad has air, well, randomly, the babies will as well. So you end up with these antennas that kind of look random, and you breed them and you get these children. Then you test the children to see which ones are good, and you keep only the good ones and you kill off the ones that aren't. And you breed those until you have several generations of antennas, and you end up with a really good antenna that you don't thoroughly understand. And that's okay. So these genetic algorithm PIFAs also work very well for implantable medical devices, although we can't tell you why each individual piece is important or not. Okay, well, that's the theory, and that's all good. And certainly we produced a bunch of these in various research labs, ours and others, and they function perfectly well as antennas. But what about actually building these and making them work? We're engineers. We need to be able to build things and get them off the bench. So when we talk to manufacturers about these, they're like, everything's great, except we can't glue to titanium. Titanium resists glue. I mean, you can glue, but it's not going to stay. You can't even solder well to titanium. So we worked with a manufacturer who actually had a really interesting process, and they rethought the antenna and the antenna design. So this is a spiral PIFA, but in this case, we wanted to be able to glue and not have to do any soldering. It's going onto a titanium case. We said it's not feasible to be soldering. So we used a feed tab, which was just coming out to a point that we would be able to feed it, and then a shorting tab that would be glued in place. And they flipped the design. So they made the substrate in a mold first. They cut out and laid a titanium, it's kind of like a piece of tinfoil in there with this feed point and the shorting tab. And then they placed the radiating element with the substrate material over the top of that, and then the ground plane or the titanium ground plane on top of all of that. And they were able to glue it just with conductive epoxy. Now, this design was much easier for them to build, much less expensive, and much more reliable as far as being able to stay together in one piece. So this was a manufacturing consideration that when you start getting too excited about your designs, just realize somebody's going to have to build this and make it work. And it was very worthwhile to talk to folks who were in manufacturing and actually building devices already, because they had ideas that we didn't. So just a shout out to people that really build things for real. Again, here are the requirements. And this is how it was done. So you put the substrate as the mold, put the radiating element in, you pour the next material in, and then you just glue, conductive epoxy it all together. Now, in this case, we actually were experimenting with designs as well. Not only the location of the feed in the ground, but realize at this point they are no longer dots, they're no longer points. Now are lines with lengths and widths to them. So we had to adjust that very carefully, as you might imagine, in order to get any kind of reasonable matching. We also experimented with cutting off the corners, some of the corners and some of the ends. So kind of this configuration number 2, the triangle, and configuration number 3. And experimented with each of these. And yeah, they were some were a little bit better than others. And then in order to test it, we put it in a jar and filled the jar with blood bank saline, which acts like human body material. And we're able to test the antenna in a fairly realistic situation. Now, you can see here that there are several different values of configuration 2 and configuration 3. They were actually both better than configuration number 1, which I don't even show here. And you can see that as you move the location of the feed, you can significantly tune the frequency of this antenna. And then we also wanted to kind of evaluate, we were using blood bank saline, how close would that have been if we had used human body material? It's close, but not exact. So we knew we had to make some adjustments there as well. And then we considered highly conductive biocompatible materials. We used platinum, iridium, titanium, and iridium itself. And the titanium was actually the easiest to manufacture, and so that was the one that was chosen. So putting this all together, we actually got some pretty good results using a shorting tab and so on. So these were the 3 antennas in their design. You can see the very best one is this one right here, which was actually a configuration number 1. Now, could we have tuned the others up as well? Most probably. You can adjust little bits of length and size and stuff, and you could really tune all these designs up there. But our best one for the frequency that we needed was our configuration number 1. And these were some of the results between simulated and measured results. Never exactly perfect, but we were pretty pleased with the radiation pattern. With the radiation pattern results. Okay, so that's all good. But we've been considering last year's pacemaker. In fact, last decade's pacemaker. Pacemakers that were 2 to 4 centimeters on the side, this kind of standard battery pack that was used both for pacemakers and is currently also used for deep brain stimulation. That's how things are today. But in the future, devices need to shrink. And in fact, the opportunities in battery technology are making it so the battery does not need to be so big, and the battery is the largest part of what's in these boxes. So if the battery can shrink because of improvements in electric vehicles, solar and solar charging, and that's where the improvements in batteries are coming from, perhaps we can use that improvement in battery technology to be able to make things like this Utah electrode array truly wireless. So that's the drive. The drive is to go from something that's 2 to 4 centimeters on a side to being able to make a medical implant that's something like 4 millimeters on a side. That's an order of magnitude difference. And that is so much significant, that's so significant in difference that it will enable a large opportunity in different types of medical devices. Devices that could be injected or put in through the veins instead of having to do full surgery. Devices that would be so small that the body wouldn't fight them and wouldn't fight them off. Devices that will fit in parts of the body we can't get to today. So the ability to go from something 2 to 4 centimeters on a side to 4 millimeters is actually here and now. Over the next less than decade, we can expect to see improvements in batteries that enable that. Well, what are we going to do about the antenna? If we were considering 403 megahertz, which is right in the middle of the mixed bands, in 3 space, we'd need 36 centimeters. In the body, we need 5 to 6 centimeters. How are we going to shrink it to get down to 4 millimeters? The things that we've done today aren't really enough. So think outside the box. Think about the tools you have available. You want something that's 5 to 6 centimeters in size, and you want to put it in the body. The body's big. Certainly, if you could choose a part of the body, you'd be able to make an antenna that's 5 to 6 centimeters in size. And how about 2 and 3 dimensions? We don't need to limit ourselves to just planes. We don't need to limit ourselves to 2 dimensions. We have the full body that we could actually consider. So one of the ideas that has come out of my group is the ability to do tattoo antenna. There are parts of the body in which we can build antennas, and in fact, which antennas have been built. In the body, you have skin, and then under skin, you have fat. Every part of your body has fat under skin, except for one area, believe it or not, your tongue. Your tongue does not have any fat under the skin, only part of your body that doesn't. Every place else, there's fat under the skin. The skin and the fat are both low conductivity materials. The skin because it's dry, and the fat because it's oily. So these are not complete insulators, but they would be considered semi-insulators. So it's a low-loss fat, it's a low-loss layer, and it covers the entire surface of the body. So if we were to tattoo an antenna near the surface, we've got all the space we need. 5 to 6 centimeters, no problem. The feed system could be placed on the implantable device, and we know that we can couple between something that's not very far, that's not very deep in the body, and the outside where we might have a large pickup antenna. So the idea is to couple through a few centimeters of tissue to connect, not physically, but through coupling, to a larger antenna that would be on the surface of the body. So here's an example where we did this with pork and the skin and fat that's shown that it's kind of yellow. That's rat skin. It's been preserved in a yellow material. And the antenna that you see is actually a dipole. See the dipole antenna right here? These are two pins, one here and one here. We're going to connect them to them on the outside of the skin. So here's just an example of the concept of being able to tattoo an antenna. So unleash your imagination and start thinking, I don't have to stay on my pacemaker body. If my pacemaker is going to be too little, can't I use other areas as well? We have a lot of materials that are available, and even more materials are coming. So keep your eye on the material science community. Biocompatible, inductive materials are already a reality, but they are getting even better. So copper tape is what we use as the gold standard. It is not biocompatible, but it is the most conductive material. So it's the best we could use for our antenna. So we used that, and then we see how everything else would relate. If we were to tattoo, we wouldn't be able to make a solid material like this copper tape, and we'd end up with a shape that looks more like mesh. So consider a copper mesh, like with holes in it, like if you'd actually tattooed your antenna. Now, a true biocompatible material is gold. So a gold nanoparticle material that's similar to copper tape is a gold nanoparticle tape, and that's shown here kind of in the middle. That is a material that's available today. Notice how its conductivity is very close to the conductivity of copper tape. The gold particles itself are actually more conductive than copper, but the material that has to hold this together is not quite as conductive. So it ends up being just a little bit less conductive than copper. And then I've included two inks here. One is Novacentrix, and that is material that is printed, and the other is Elcoat ink, which is painted on like with a brush. Now, neither of these are biocompatible today, although the material that's used to hold these inks together, the particles are silver in both of these cases. The process by which this is made, they could be made with a biocompatible material. So it would be feasible to make inks that are biocompatible. Notice how the inks have a conductivity, something on the order of 10 to the 5th, which is about a factor of 100 less conductive than the coppers and the golds. So this really does impact our antennas, but all of these are feasible. So they could ultimately be developed so that they could be used in order to construct antennas. Now, let's see what happens when I use these different materials. And this is just in free space, so I didn't have to worry about body materials or anything. So I'm just testing the effect of the conductivity of these materials. The copper tape is the gold standard, and that is this red one right here. So copper tape is the gold standard. Notice that the copper mesh is not very different, and the gold nanoparticle material is probably the next closest, followed by the silver ink, the Elcoat, and then by the Novacentrix. All of these materials would produce reasonable antennas. And so it's good to know that we actually have several materials that could be developed for producing implantable antennas. Here's an example of a tattoo test where we actually measured the thing. This was done with Elcoat ink and a couple of pins connecting onto the antenna. And you actually do get a feasible antenna in the range. Let's consider now copper tape versus gold nanoparticle. The time I was using the copper tape and the Elcoat ink, I didn't have the collaboration that I do now in chemical engineering. And as soon as I met folks that were working with gold nanoparticles, like, oh my goodness, this is a really cool material. So notice how close the gold nanoparticle and the copper tape are together. Remember, the copper tape is our gold standard, and the gold nanoparticle matches that, very, very closely. In fact, even slightly better in some of the frequency bands, the band that we cared about. So the gold nanoparticle is already available, and in fact could be produced in a way that would be biocompatible. What it can't be yet, although that is coming, is injectable. So to be able to be tattooed. At the moment, it has to be made into its foil outside the body because of the heating required. But methods are coming where this material is going to be injectable inside the body so that it could be used for antennas of this type. So if you're working in biocompatible areas, keep track of the material science community. There are some really exciting things that are coming down the pike. Well, now let's imagine a little bit about the current distribution. So this is an antenna where we wanted to consider just how much insulation was needed. So the antenna on the top left is showing the current distribution when this antenna is in direct contact with the pork. Notice how the current really isn't making it out to the tips of the antenna. It's getting shorted out. It's being held very close to the feed point. So this antenna would not be ideal. Putting the antenna in direct contact with the pork, yep, we're getting shorting out just like we thought we were. Now let's go over to the one on the right where it has just saran wrap. That's just plastic wrap, really thin in between the pork and the antenna. Well, the energy is getting out a little bit further. It's not shorting out quite as badly, but it's certainly not really getting to the tip. Part of this has to do with the electromagnetic coupling through the saran wrap. So the saran wrap is a plastic. It is preventing the direct shorting out, but it's not preventing the electromagnetic shorting out. So we're still getting some level of shorting at this case. Now let's put our dipole antenna with a fat layer, and notice how the fat layer is making the current go virtually all the way out to the edges of the antenna. So the fat layer is acting as a good insulator for this antenna. If I add saran wrap to it, it doesn't change things very much. So really the fat's the thing that's doing a nice insulating for me. So that fat layer, that's a good idea. Well, here's what's coming in the material science community. I mentioned, I've said several times, there's a material coming. And here's an example of what that could be. So a biopolymer is a material that can be anything between a fluid and a gel, could even come to a near solid. And the way that is done is by using a polymer chain, and that's kind of these wiggly things that are shown here, with a crosslinker. A crosslinker, the arrows, kind of holds the polymer chains together, and that makes things more solid. If you were to, so an example of this would be epoxy, where one of the materials is a polymer, the other is a crosslinker. You mix them, and it goes from a liquid to a solid. The same thing is going to happen here. But if you took the crosslinker and you encapsulated that in a plastic or a glass capsule, and the two things wouldn't be mixing at this point. But if you were to break open the capsule, that would release the crosslinker, and the thing would go from fluid to solid or a gel. Now, this can be done with heat if you make the capsules so that they can be broken by heat, and in fact, broken by the right amount of heat. You can control the temperature at which these capsules break. So you can take a polymer and a crosslinker. You can encapsulate the crosslinker in a capsule. Basically, you just bubble it through, like you literally bubble it through the encapsulating material. And then you could use any kind of heat. You could use the body heat. You could use focused hyperthermia. You could use HIFU in order to break the capsules, open up the crosslinker, and allow the material to gel. So you go from a fluid to a gel of about any solidity you want. The more crosslinker, the more solid your gel is going to be. So this is a material that's being developed by my colleague in chemical engineering, Huan and Zhang, and it's pretty darn cool material. Biocompatible, injectable at low temperatures, and then can be converted into a gel at higher temperatures. And here's an example of us testing that material. An RF cardiac ablation probe is a radio frequency probe working between 350 and 500 kilohertz. And it's just an open-ended coax, and it's used to give RF energy into the heart in order to be able to cauterize parts of the heart in order to be able to handle different types of cardiac problems. So here we've taken a cardiac ablation probe because it's giving us the frequency that we want, and we've put it into a vial of this polymer that you see. And you'll notice that there is a droplet. It's hard to see because it kind of it splits because of the optical illusion here. Here is a solidifying droplet on the end of that probe, and here's a droplet from a previous example. I'm going to show you a video of this. So watch, I think let's hope it plays. Yep, here we go. So watch what's going to happen right here as we see it solidifying as we add RF energy. And what that's doing is basically heating the polymer, releasing the capsules, and allowing the crosslinker to solidify the material around this probe. Okay, so what could you do if you had a polymer that could be highly conductive, injectable, and could be cross-linked to solid? What if you could inject an antenna in the body? What kind of antenna might you inject? Just imagine taking a needle and injecting an antenna into the body. Now, here's another basic premise of electromagnetics. We know that fields concentrate on pointy things, on tips. We also know that they concentrate in small gaps. What if instead of even limiting yourself to the fat layer, instead of limiting yourself to being planar, what if you truly thought 3-dimension? What if you used a needle, a hypodermic syringe? And what if you injected that little tiny 4-millimeter device into the body? And what if you followed that with a bit of the polymer? And what if you heated that as you went and you actually made a wire-like antenna? So inject your medical device and inject your antenna right behind it. Here's how that might work. You might use an open-ended coax that has a hollow core. The hollow core can be used for injection. So you might inject the device, and in fact, you might inject the fluid to create this biopolymer antenna at the same time. By adding a little RF energy to this probe, you can heat the polymer that you have just deposited, basically extruding a wire as you leave it there in place. Now, would you really want these to be wires like solid? No, you'd like these wires to be somewhat gel-like, like the same physical properties as the material that you're putting this in. So kind of a soft jelly material would be left behind to be the antenna. And that would concentrate the fields from outside. It would gather them up, and it would focus them down on the implantable device, allowing us to use, again, a very small antenna on the implant. So this was another kind of creative idea for using a focusing antenna and not limiting yourself to just 2-dimensional antennas. So when we think about next generation implants, the implants we have today, they're being served by antennas, and we can improve them, of course. But really what's next generation is an entirely different set of medical implants that don't require full surgeries, medical implants that might be implanted by injection or that might be implanted up through a vein. So being able to go from the idea of using a battery pack that's 2 to 4 centimeters on the side and shrinking it down to something that's only millimeters on a side is where the medical implant community is hoping to go next. And we, those of us that are designing antennas, need to go right along with them. The concepts we have today for the simple traditional antennas aren't enough, and we need to really get creative with our designs and think outside the box, come up with ways to make antennas that can work for very, very small medical implants. And so that's what I wanted to share with you today, and I'd be delighted to discuss any questions.
Thank you so much, Professor Furse, for the interesting talk and for the devoted time. So now we'll open the floor for questions.
I'm happy to see either chat, or feel free to unmute, and your questions are always great. Well, do you want me to start with a question? So remember I told you about the SAR guidelines that make sure that we don't put too much heat in the body, and yet I've just proposed putting in a design that actually heats inside the body in order to produce the antenna. This remains a challenge. We need to be sure that we can produce a device that doesn't burn the tissues around it, even while it's heating the antenna itself. A coax is pretty good this way because the outside of the coax doesn't heat much at all, but that's going to be one of the significant trade-offs in this device, is how quickly can we heat the polymer so that it doesn't flow away compared to how much we might burn the body. So these things are not prime time. They're not ready to be sold today. There's still an awful lot of research to be done.
I have a quick question, and then I have to run, but this was a very nice talk, and I think I really appreciate, and I think the students probably also appreciate that it was very explanatory in terms of you spent a lot of time introducing the field and how these things work and why they're important. So I think that is definitely very, very highly appreciated. So regarding, this is in a similar vein as the points you just mentioned about the specific absorption. So for some of these antennas, which are more so going to be created or basically built up as they go along, like with these polymers, for example, those, how do you envision sort of the approval process? Because I know when it comes to these types of new implantable devices, it can take a really long time to get these things approved, even if you verify in the laboratory that it's safe and it works and so on and so forth. And as a tangent to that, so for example, the last device that you showed where you're creating the antenna sort of as a needle as it's going in, is there an easy way to remove that if need be? Because you're kind of sort of embedding that within that layer of fat and it goes into the muscle, and then it's kind of like you're making a needle and then just breaking it off in there. So would removal also be potentially tricky if you need to sort of, for one reason or another, remove the implant?
Well, you have hit on two really important aspects of medical devices. The first is that approval of anything medical is a very long and extremely expensive process, non-trivial indeed. One of the particular challenges of this type of device would be that it's not just one, I mean, you just don't build one of these, you don't open it up, take it out and plop it in. Each antenna might physically be different. You might have injected a little bit further or a little bit not further. So it may actually require a robotic assisted surgery in order to have the precision to enable this to be approved at first. Now, as far as removing this, it's definitely a problem, especially because this wouldn't really be like a wire. You can't just get hold of it and remove it. You can't even cut and remove it. So one of the things that those that are working in biocompatible materials are concerned about is the ability to make the material break down and reverse the cross-linking. The way that would commonly be done is to have pieces in the polymer chain that can be broken with perhaps additional heat or another frequency. These materials do not yet exist, but it's definitely a concern for those that are developing biocompatible materials. So you have hit on two key challenges that remain.
That makes sense. And then you would definitely want, when it's broken down, whatever is encapsulated inside it to also be able to get safely absorbed by the body. If you have metals, for example, right, you would want the quantity of those metals. I know there are certain metals which are biocompatible, but then in large quantities, they could also potentially be toxic. So I'm guessing that's also a safety concern potentially as well. But this is all really cool. And I think it's also super important to be thinking about this, because as you mentioned, as the electronics get miniaturized, then you get smaller and more advanced chips that are lower power, and you also get higher battery density. You still need to communicate, right? And so you need to have a way that you can efficiently do that. And I think it's very timely to be thinking about these things. So this is very cool stuff.
Thank you.
Professor Furse, we have a question from the chat. So I read it. Sonem, he said, like, thank you for your presentation and the insightful information. I have a couple of curiosities regarding temperature activated polymers. What potential applications can there be from antennas with these polymers? I saw in the slide about a polymer that becomes a gel at 40 degrees Celsius. Are there materials existent with activation temperature near room temperature?
Super interesting question. The material science community is very, very busy on this. And whether you need it to be biocompatible or not, those that do not need to be biocompatible are ahead of those that do need to be biocompatible, as you can kind of imagine. So there is a way to be able to adjust the temperature for all of these cross-linkers, including those at room temperature. Again, epoxy would be an example of that. So how they change the encapsulation as how you control what's going to cross-link and what isn't. It may even be possible to break the cross-linker capsules with something like ultrasound at room temperature. So yes, there are different temperatures and there are ways to control the temperature via the encapsulation. I do not know of a biocompatible material that is highly conductive, that is able to gel at room temperature, but I do know of some that are able to be biocompatible and partially conductive at body temperature. So just being able to inject it and not having to add another source of heat. The challenge is being able to make it conductive at the same time. Basically to align like long particles like gold nanostructures, for example, to be able to align those so that they all line up and kind of touch each other, making a conductive mesh inside this polymer. So these materials, again, are coming, but not here today. So No, I don't know of a biocompatible material that would do this. There are apparently polymers that can do this. It's well worth having a colleague in material science who works in these areas and can help develop and or guide you on these materials. But there are additional materials coming. You'll see a lot in the flexible electronics literature. So just watch what's coming. More is coming and coming fast.
Cool. Another question is if you can comment on the security aspects of the implantable devices transmissions.
Oh, yeah. So security and privacy always are going to be an issue. Security in many cases for medical reasons. Like you wouldn't want to, suppose you had a world leader who had a pacemaker and you could shut them down just by, running an electromagnetic field that would destroy their pacemaker. That would be a bad idea. So certainly security and privacy are two really important things that you have to consider when you have all devices and implantable ones especially. That is not so much handled in electromagnetics to date. I haven't seen a lot about antennas trying to be, so secure. You certainly have to keep them narrow enough bandwidth that they don't allow extra frequencies in, but broad enough bandwidth that they allow only the frequencies that you do want. So there is certainly this to work with. But more security things would be done by the signal processing groups, being able to have various data security protocols in the data itself. So the fields may get corrupted. You evaluate the data and see if the data got corrupted. And that's how you decide if you're going to use the data or not. So definitely security is a consideration. Again, I haven't seen security protocols or security solutions physically in electromagnetics, but certainly in the data processing. And yes, it is a really important concern.
Yeah, thank you. Then please, for attendees, if you would like to ask questions, feel free to just speak. And if not, thank you so much for your time, Professor Furse.
Thank you. Thanks for inviting me.
Yeah, it would be great to see you in person, at some point.
So come to the Antennas and Propagation Symposium in Portland, and hopefully I'll get to see at least some of you there.
Yeah, in July, hopefully.
Yep, in July, yep. So,
okay, then. Yeah, okay, then thank you so much again. And it was our pleasure to have you. And thank you all for attending the talk. And please make sure to follow us on LinkedIn to be up to date of our future events. Thank you so much.
Thank you. Have a good night.
Yeah, have a good night, Professor. Bye.
Bye-bye.
Thank you. Good night.